Hello, my name is Kobe Scheidemantel, and welcome to Team 21066's Design Day video presentation. Team 21066 has been hard at work creating an automated pressure regulation system known as the APRS for the space analog for Moon and Mars at the Biosphere 2. The sponsors of this are the Biosphere 2, Over the Sun LLC, and the representatives are John Adams and Kai Staats. I will now be handing off to Gustavo to describe the overall design.
Hello, my name is Gustavo Aguilar-Velez. The APR system is a prototype built at a 1/10 scale of the one currently being built at Biosphere 2. Due to the sizing of the compressor, we had to house it outside of the APR's living crew quarters and build a cage where we could easily access all the features of the place inside the full-scale design. The hardware for the prototype includes the compressor, the different sensors, the mock living crew quarters, the GUI display, a utility wall, and an emergency release valve.
Hello, my name is Megan Marlowe. The utility wall is located on the side of the scaled living quarters and has 6 input holes for air fittings. 5 of these connection ports are 1/4 of an inch, while the 6th is 1 inch to support the inclusion of an emergency release valve in case the pressure exceeds +2 psi over ambient pressure. Here we have the process flow diagram, which has been divided into 4 color groups. In the full-scale model, all of the components except the air tank would be inside the quarters. Due to the small size of the prototype, all components are outside the quarters. The flow starts from the utility wall that is attached to the living quarters and travels to the depressurization system, shown in yellow. Here we have the compressor and a particle filter, which collects moisture from the air. A manual valve is connected to the filter for water reclamation. Next, we have the blue group. A check valve is used to stop reverse flow, and it is connected to a cross connector along with a pressure monitoring system and air tank with a manual valve. An analog pressure gauge is included for redundancy purposes, so if the pressure sensor breaks, the pressure can still be monitored. From there, we move to the red group, where there are 3 lines. The top line has a single solenoid valve which allows air to move from the tank to the quarters at full force. This is used when fast pressurization is needed, such as leaks or sudden pressure change. The middle line has a pressure regulator which drops the pressure to 1 or 2 bars for a more stable pressurization. The bottom line has a manual valve for redundancy purposes, so if the system powers off, positive pressure is still maintained. The green group consists of a pressure monitoring system for the quarters and atmosphere, and valves to release excess pressure to the atmosphere.
Hello, my name is Ahmed Al-Raisi. For the software of the APRS system, a Raspberry Pi is used to help automatically obtain the +1 psi difference between the inside pressure and the outside pressure of the habitat. A GUI gives the user an opportunity to either have automatic control of the system, where the system itself maintains a +1 psi difference, or gives the user manual control of the system. The system contains different pressure sensors to measure the pressure inside the mock living quarters and the pressure outside. A pressure differential sensor is used to measure the difference between the inside pressure and the outside pressure. Data from the different sensors are transmitted into the Raspberry Pi in order to automatically maintain the +1 psi difference. This is the circuit or wiring diagram of our system. There are 2 different voltage sources, one AC and one DC, which would be from an adapter. The AC powers the compressor and solenoid valves through the relay. The AC ground is connected directly to the devices, while the AC power has a relay between them. The DC powers the Pi, the relay, and the sensors.
Hello, my name is James Marlar. The system block diagram and the system architecture is shown here. The system architecture shows the breakdown to our 4 subsystems: the sensor array, the GUI display, the compressor, and the utility wall. These are all within the pressure regulating system, and the block diagram shows how they interact with each other. Each system requirement flowed down to one of our 4 subsystems into our system. Each requirement was allocated, derived, or directly assigned to each subsystem to ensure all system requirements were met and nothing was missed.
The living quarters were fabricated using 16-gauge mild steel that was welded around a frame from square tubing. An airtight environment is required for final testing and validation portions of this project. Preliminary testing was done after the living quarters were initially welded and checked for leaks to ensure an airtight seal was achieved.
Hello, my name is Arhanu Misono. A
compressor system with air tanks to add or remove air is connected to the living quarters via the utility wall. The compressor works hand in hand with a solenoid valve that rapidly moves air through the system. As mentioned previously, the valve moves the air from the tank to the living quarters and is most effective when we have leakage or sudden pressure changes in our system. As the rate of increase is fast, the relay will turn on a solenoid valve that releases excess air into the outside environment. Within the system, we also decided to integrate a non-relieving pressure regulator with the purpose of maintaining the air within the system while still being able to control the pressure going into the living quarters.
An absolute pressure sensor reads the pressure inside the living crew quarters. To ensure the pressure of the target +1 psi differential, a differential pressure sensor was used to read the difference between the internal and external pressures. This pressure difference data is key input for the software controlling the APRS, so a more accurate sensor was required. The chosen differential pressure sensor is more accurate in comparison to the absolute pressure sensor. With many differing pressures on the Moon and Mars, we need to make sure that differential reading remains constant to reduce the chances of a sudden change in internal pressure.
For the prototype to be successful, both hardware and software are important in designing the APRS. Python was used for the APRS software code since it is versatile and it is widely used for engineering projects. The main inputs to the system are internal and external pressure, and the data is delivered by the various sensors. The code uses an array of Boolean variables to control the relays that are controlling the system. Each index of the array is associated with a relay, and each relay turns on or off the different solenoid valves. The APRS works in an infinite while loop and is considered a semi-closed system since air is circulated in the APRS. The flow of the air circulated in the APRS is broken down into two paths. Path 1 is when air is released and captured into the living quarters and excess air is stored in the main tank. The second path is where the system releases excess air to the atmosphere.
As a team, we had to perform various tests to validate the system. For example, we tested the compressor's performance in the compressor practical use test. When an initial test was performed, the compressor was not compatible with the system, resulting in a performance failure. From there, the system was redesigned and an additional pressure relieving line was added from the filter to the living quarters to address the compatibility issue. After implementing these changes, the test was reperformed and the compressor was deemed compatible with the overall system and the test was passed. After the system was fully assembled, it was put through a system response test where the system ran on a 24-hour cycle and the pressure was monitored every 10 minutes to make sure that the living quarters stayed at +1 psi. The result of this test was expected. With slight overshoots on pressurization and depressurization within a reasonable scale, the system performed well. This test was crucial to showing the actual performance of the system under normal conditions. With the help of our sponsors, the team was able to create a working prototype of the APRS. Through system and subsystem testing, APRS was validated and all system requirements were met. Thank you for watching our Design Day video and covering the APRS.